We are now on to stage 4. This is core practical skills and manipulating data, writing up experiments, and so on. So typical marks lost in this, quite a few. Usual culprits would be vague descriptions, not identifying variables. The uncertainties is a big part of this, and you need to be really, really confident with that. We will look at a practice question on uncertainties later on. Poor evaluation and misunderstanding data and graphs. So examiners' comments on this. So very often examiners will say that there is some description, but there's not enough detail or quantities. So it's a bit too vague. And very often students will say, plot the data without talking about, well, what do you plot and what does the gradient represent? So a lot of this is to do with detail. So I've come up with an acronym, which is SMART. We like SMART targets. So we have SMART, so the S would be setup. So this is just the basics, getting the basics right. So what is the equipment? Maybe draw a diagram, maybe describe the apparatus. So a lot of students tend to get that reasonably okay. The measurements is really important, and a lot of students miss this out. So what are the variables? We could talk about the independence, the dependent, and the control variables. What is measured? That's normally mentioned, but students nearly always forget with what instrument. So we measure the length with a ruler. We measure the diameter with a micrometer. That's really important. Very often students will just say, take some measurements. They won't say, what is the range or the increment? They often forget the really obvious thing to just say, repeat and find the average, and they usually don't mention the units as well. The analysis is really important. Very often students will just say, as we mentioned, plot the data, but they won't say, well, what do you plot on the y and the x-axis? What would we expect to get? What does the gradient represent? And maybe any calculations or reference to formula there, that would be very important. This is a really key part of it, the uncertainties, and very often this will actually be a separate question. So you have to be very, very confident with identifying causes of uncertainty, calculating percentage uncertainties, and combining percentage uncertainties. So we will go through an example of that later on. What are the sources of error? How do we reduce the sources of error? How do we improve reliability? And then the theory is really important. What are the formula? What are the principles? What is the expected relationship? Would we expect it to be proportional or inversely proportional? So we're explaining the results using physics. So the key quote here would be that these questions are not easy, but they are predictable. Certainly the ones we are asked to describe a practical investigation. So you should, with practice, get good marks on these exam questions. So let's have a look at a typical exam question. So you might want to pause the video here and try and answer it, see what you come up with, and then we'll have a look at a typical student answer. So here we go, let's have a look. So we've got a percentage uncertainty calculation. So we're given various values and their uncertainties. And sometimes it might ask us to find the actual value, but it doesn't. We're only focusing here on the percentage uncertainty. So find the percentage uncertainty and resistivity. So we will need the formula for that. And then part B is more as expected. Describe a practical investigation where we get a better or more reliable value for resistivity. So let's have a look at a student's response. So this would probably be a grade C, maybe grade D overall. So let's go through this. So this student starts off quite well. So the first 3 calculations are fine. They've worked out the percentage uncertainty, so just the uncertainty divided by the quantity multiplied by 100. So there is some discussion about whether your value should be limited to 1 significant figure. That would be good practice. Most examiners would accept 2. If you've got 3 or 4 significant figures, then you would start to lose marks. So they've identified the resistivity formula. So we've got that. Percentage uncertainty, we need to combine the percentage uncertainties. They've just added them all together, which would be fine, but the diameter, if we're calculating the area, this is going to be pi r squared, or if you prefer, pi d squared over 4. So because we're squaring, then we have to multiply that percentage uncertainty by 2. They've missed that out. So when they identify, they say the resistance is the largest, but that's not going to be true because this is going to be 3.1 multiplied by 2. So they'll probably lose 2 marks there, maybe even 3, depending on the mark scheme. So part B says a more reliable, so basically a better value for resistivity. So rather than just a single value, which we know is prone to error and is not good practice, what we need to do is to measure a range of resistance and length values. So measure the length of the wire and the diameter. So they haven't identified with what, so that's marks lost there. Measure the resistance with a meter. They haven't identified which meter. It should be an ohm meter. Calculate resistivity. Well, okay, so they're just doing a single value here, which is not good practice. This is not what we do in the core practical. We get a range of values, we plot the data, and we work out the gradient. So that they've missed out there. Repeat a few times, a bit vague, find the average. They might get a mark for that. Try to be careful and make sure measurements are right. Very often students write that, which is rather sweet, but that won't get any marks because they haven't specified precisely what they're going to do. So out of 5 marks, 1 or 2, possibly, they've missed a lot of information there. So yeah, that's not a good answer at all. So let's look at a better answer, a model answer. So you might want to pause the video here and have a read through this, and then I'm going to highlight all the key points. So as we said before, the length, the diameter, the resistance, these are all fine. So we've left these as 2 significant figures. The resistivity, okay, so we've got pi r squared or pi d squared over 4. So we're going to have to multiply 3.1 by 2 in our calculation, so we get this larger value here. 10.7%, that might be problematic. You might want to round that to 2 or even just 1 significant figure. That might be best practice. And then we've identified correctly the diameter has the biggest effect. And why? Because we're making that absolutely clear, although we've shown this mathematically, because of pi r squared, we have to double the percentage uncertainty. So that would get us our full 5 marks. For the practical investigation, so we've measured the length of the wire using a meter ruler. It's such an obvious thing to say because, well, what else would we use? We always use that, but by saying that, that could guarantee that mark or maybe even get an extra mark. And we've identified the range and the increment. So from 10 to 100 centimeters every 10 centimeters. So it's very, very specific. Measure the diameter of the wire multiple times using a micrometer. So we've identified the instrument. Why do we do it several times? That's to find the mean diameter. That's to reduce random error. And we could talk about converting that to meters. That's quite useful. Measure the resistance. We could do an ohm meter, that's fine. If you want to use a voltmeter and an ammeter, you could do, but then you'd have to do the calculation at R equals V over I. Repeat again 3 times, find the mean. Why do we do that? So we're understanding that's not just because that's what we've always done, and that's good practice, that's what the teacher tells us to do, because it reduces the random error. So sometimes the values are too big, sometimes they're too small. By calculating the mean, that reduces the random error, so that extra detail. We could talk about the variables. So there's only should be 2, to make this a fair test, there should only be the resistance and the length. Everything else should be constant, so the equipment, the temperature, make sure the wire is straight. So don't just say plot the data, that won't get any marks. Plot the resistance against the length. So resistance on the Y, length on the X. So resistance is, so length is the independent variable, resistance is the dependent variable. Calculate the gradient of the line of best fit. And then we've got the formula, and we equate that to y equals mx plus c. So if r is the y variable and L is the x variable, then m represents rho over a. So rho is equal to the gradient multiplied by a. Really, really important. Very often students just say, plot the data and use it to find the resistivity. So you're losing a couple of marks there. So we probably don't need to talk about uncertainties in this case because part A has mentioned them. But if there wasn't a part A to this, you could talk about uncertainties, which is the largest source of error. There's not particular safety issues in this practical, but in another practical you might want to talk about safety issues and wear safety glasses and so on. Right, that's stage 4. So do have a look at the practice questions in the booklet for stage 4, and I'll see you next time.